Okay, so this is the second part of our review in unit operations. And the processes that we are going to cover are the separation processes. So for this first set of slides, we'll be covering gas equilibria. That is in the case of gas absorption and stripping. Then we'll have, of course, before that, the concept of phase equilibria. Then we'll have adsorption and extraction. The other processes will be discussed in the next set of slides, I think, which will cover leaching and distillation. And I think together with membrane separation. Okay, so let's start with phase equilibria. So this is the topic that governs the separation processes in the sense that actual mass transfer ceases when equilibrium is already reached between the phases that are being conducted. So not that there is a complete stop in the operation of the transfer. It's just that the rates of the transfer are equal, and as such, there is no negligible change in the concentration of the component that is to be transferred from one phase to another. Or let's say in the case of, for example, gas absorption, so when equilibrium is already reached between the gas phase and the liquid phase, there won't be any transfer anymore from the gas phase to the liquid phase, which is the solvent of the component that is to be transferred. Now, in the case of phase equilibria, so as mentioned already, mass transfer ceases when equilibrium between the two phases is reached. And the rate of mass transfer in this case is directly proportional to the driving force, which is a departure from the condition of equilibrium. Now, to be able to evaluate this rate of mass transfer, the driving force has to be accurately determined, which is in turn relies on the equilibria between the phases. Now, in nearly all situations, two phases are involved except in the case of two solid phases. So the controlling variables for phase equilibrium are as follows. So we have the intensive properties, temperature, pressure, and concentration. So these three does not depend on the amount of the system or systems that are being conducted. Contrary to that, so these are actually the operating variables which needs to be fixed. That way, whatever is required by our problem or by a particular problem, we're able to solve it. So anyway, later on, we'll be discussing about variance, or this number of variables that needs to be fixed. That way, we can solve for the required information in the problem. Now, the equilibrium data, if you can recall, can either be taken from the table or from a table, from a graph, or it could be expressed in terms of an equation. Okay, so this we will cover in the next slides. So for most operations, however, the pertinent equilibrium relationships are shown graphically, or we extract the relationship, for example, between x and y from a graph. We can also see it in the table, or we can also have this relationship between x and partial pressure. Can also be taken from a particular graph. So most of the time, since for a particular system, we don't have the actual tables of relationship between x and y or x and PA, but the graphs we do have. So whichever of the two is available, so you use it. That way you can get the needed information that you need to substitute to a parameter in an equation. Okay, as to the basis for phase equilibrium, as mentioned a while ago, so we have this phase rule. So the F we determine, this is the variance that I was mentioning a while ago. So the number of degrees of freedom or variance, which is dependent on the number of components in a particular phase. In our case, we limit it only to two component systems and the number of phases that needs to be conducted for a particular separation process. So number of phases, so in the case of gas absorption, again, since that would be the first topic that we will be covering, we have two. We have the gas and the liquid phases. Now, these degrees of freedom or variance refers to the number of independent intensive variables. They were mentioned a while ago, temperature, pressure, and concentrations that must be fixed to define the equilibrium state of the system. If fewer than f variables are fixed, meaning the problem only gave you less than the computed f for such a problem to be able to solve, so an infinite number of states fits the assumption. Now, while if f is too many, the system is over-specified. So we seldom encounter this situations rather wherein your f is less than or greater than the computed f. Most of the time, we have it given already as to whatever is the computed f. The number of degrees of freedom or independent intensive variables really is equal to the computed value based on the phase rule. Now, for a two-phase system, which is the case in our separation process, we don't cover multi-phase systems. Variance is always equal to 2, which is also equal to the number of components in our system. So, for example, if most of the time the problem have the pressure fixed or it's specified by the problem, one of the concentration, either the liquid phase concentration or the gas phase concentration is given, then the problem would ask you for the other one. So if you're given the liquid phase concentration, the gas phase concentration would be asked, or vice versa. So in this sense, the number of independent intensive variables is equal really to the computed variance. So in terms of whether it's possible to determine the solution to such a problem, the answer is, of course, yes. Now we have Riots Law. This is for ideal systems only. Gives you the relationship between mole fraction in the liquid phase, which is represented by X, and the partial pressure of A in the gas phase, which is the small p sub A. Now in some books, the capital P sub A has a naught. So P sub A naught represents the vapor pressure of pure A. Sometimes it's also represented by A prime. So P sub A prime in that sense. But in this equation, this particular vapor pressure of pure A can be taken from a equilibrium relationship table. So you can get it from a table, or you can also get it from an equilibrium diagram. So Riots Law, as mentioned already, only holds for ideal solutions. So the problem has to specify that your system is ideal. Okay, so benzene and toluene is one such system. That is why it's often used in problems or in sample problems in our main reference books. Now, if the system is not ideal, then we have the option to use Henry's law, which in lieu of the pure vapor pressure of component A, now this time we use the Henry's law constant, which can also be taken from a property table based on the system that is given. And using the operating temperature, we get or pressure, whichever of the two is given, excuse me, we can get the required information. We can get the Henry's constant, and after that, of course, we can use this equilibrium equation in the problem together with the material balance equations. Now, from Henry's law, we can have this derived, the relationship between mole fraction in the liquid phase and in the vapor phases, XA and YA. And of course, our Henry's law constant need only to be divided by the total pressure of the system. If the problem is silent about the total pressure of the system, automatically it's assumed to be the atmospheric pressure. So dividing this original equation of partial pressure and mole fraction in the liquid phase of component A by the total pressure of the system leads to this equation here. Okay. The next is, of course, the K factor or the distribution coefficient. You will be able to encounter this particular concept in McCabe. Now, this is the ratio of the mole fraction of a particular component. In this formula, you get to see it to be component I in the liquid phase and in the vapor and in the liquid phases. So what you have in the numerator is the vapor phase composition, and in the denominator you have the liquid phase composition. Take note that in the subscript you have E, denoting that these are concentrations measured at equilibrium. Now, if your system is ideal, you have another equation that you could use, or formula that you can use for the distribution coefficient. And that would be the ratio of the pure, so I'm using here the prime, the pure vapor pressure of component I divided by the total pressure of the system. In this case, you are determining the K factor, or the distribution coefficient, based on component I. Again, if Riots Law holds, we have this relationship between the K factor, or the distribution coefficients, based on components I and J. So if we take the ratio of these K factors, that would also be equal to the relative volatility of our system. So the relative volatility of component I with respect to J. If we change the manner of writing the subscripts here, class, let's say you write first the Y and then followed by the I, then you also interchange this one. You also interchange the subscripts here and also in here. Because the manner we write the subscript for relative volatility really matters in terms of the formula that we are using. So relative volatility of component I with respect to J. So if it's lambda sub Ji, so relative volatility of J with respect to I. And that would only be the reciprocal of the previous relative volatility. So you have here ratios again of the mole fractions measured at equilibrium. So I did not anymore write here at equilibrium, because anyway you have it in here. And then it could be the ratios of the two K factors, or distribution coefficients, or even the ratios of their pure vapor pressures. Now that's for the relative volatility. So in this case, you really need to know the temperature. Now, K factors are strongly temperature dependent, so meaning they change with temperature. But relative values of K for two-component systems change only moderately, or the change is very negligible. So as such, we still consider it to be a constant if we have a two-component system. Now, that's in the case of the K distribution factor. So these are actually the equations that tells you the relationship between variables at equilibrium, or that specifies the equilibrium condition. Now, in terms of equilibrium diagrams, so these are the equilibrium diagrams that expresses relationships also. So this one is X or Y in terms of temperature. This is used in distillation. This is XA in terms of YA, also used in distillation. And this one is liquid, so XA, and partial pressure. So this is used in gas absorption. Okay, this is limited only, so whatever is the system that is defined in a particular diagram, that this diagram will only be applicable to such system. If we speak of a different system, of course we should be using a different equilibrium diagram. Now, in terms of table, I think you're familiar with this. This was shown to you in phase equilibria last year. So this is the temperature column. This is the vapor pressure, the pure vapor pressure of benzene and toluene based on temperatures here. And you have two sets of values for different units. And you have here the relationship between XA and YA for this system, benzene and toluene. Okay, so you can either use tables, equilibrium diagrams, or equations. That way you can get relationships between the variables that you want the relationship of. So that way you can use these relationships where in your material balance equation whenever the need arises. I have sample problems here. I'd like to go back to the sample problems when I'm done everything in this set of slides. That way I have covered everything. Okay, so we'll just skip it for now. We'll go back to it when I'm done already with the rest. Now we go to gas absorption and stripping. So when we speak of gas absorption, it's this unit operation in which the soluble component of a gas mixture is being dissolved in a liquid. So your feed is the gas and your solvent is liquid. So the inverse of gas absorption is called stripping or desorption. Now the transfer this time is from the liquid using a gas or solvent. So that involves the transfer of desired volatile components from a liquid mixture into a gas. So both absorption, stripping, and distillation have something in common in that they use this special equipment to bring the gas and liquid phases in intimate contact. So as discussed, your columns, these columns in which these unitary processes are carried can either be in the form of packed columns, tray columns, or spray columns, even bubble columns, all of which are present for the three processes. But oftentimes, it's the packed column and the tray columns that are being used. Okay, now we'll review them later as we go through that, we reach that particular portion. Now, absorption, stripping, and distillation operations are usually carried out in vertical, cylindrical columns or towers in which devices such as plates or packing elements are placed. So I mentioned already, the gas and liquid normally flow countercurrent, and the device serves to provide the contacting and the development of the interfacial surface through which mass transfer takes place. So in the process of interacting the phases, there is this development of the interfacial surface where real mass transfer occur. So if the manner of contacting, or let's say the time of contact, is insufficient, there won't be the establishment of this interfacial surface, which will of course make separation not 100% or near 100%. Now, for gas solubility, this is an equation taken from the handbook. This allows you to determine the solubility of gas in water. So if the solvent is not anymore water, this particular formula will not work. So this is only for solubility of a particular gas in water. So you have here mole fraction of gas A in the liquid phase, and you have here the molecular weights of A and that of water. Okay, so how soluble is a particular gas in water only depends on its mole fraction in the liquid phase, because the molecular weights you can anyway take from a periodic table. And we have sample problems here. I will discuss it as well later. Now, for the equipment selection, so plate columns may be economically preferable for large-scale operations. So take note of this, and are needed when liquid rates are so low that packing wouldn't be adequately wetted. So there won't be enough contact because the liquid rate is small or low, that your packing material will not be proper, or shall I say, sufficiently wetted. So if it's sufficiently wetted, then there's not enough surface or interfacial surface that will be established for mass transfer to occur. And that is why for large-scale operations, it's the plate columns that are preferred. So plate towers may have a better turn-down ratio and are less subject to fouling by solids than are packed towers. Now, these packed columns usually are chosen for very corrosive material. So though plate columns is preferred for large-scale operations, if the material to be handled are corrosive, or if the liquid tends to foam, or it could either be a small or large diameter tower involving very low allowable pressure drop. So there's a need for the operation to be operated at a delta P, which is small. Then we can use the packed columns. So since the plate column is for the large scale operation, then the packed column for small scale operation. Okay, so the diameter is even less than 2 feet. So you can imagine a column with a diameter of less than 2 feet. So take note of the application of the two types of towers or columns for gas absorption. Now, this is how we number our gas absorption diagram. So if it's gas absorption, we number plate 1 or stage 1 on top because our liquid is introduced on top, which is our solvent. Now our feed is introduced at the bottom, and that's where stage N is. So these two flow countercurrent to each other. The labeling that you see here is based on John Couples. Okay? John Couples labels the phases based on the tray or the stage where it came from. So since this is coming from stage 1, so this is V1. Since this is coming from stage N, this is L1. Since this is to be introduced on stage N or plate N, then this vapor or this feed gas mixture is coming from stage N plus 1. So that's how John Couples labels it. This is your solvent coming from stage 0 because it's being fed to stage 1. For McCabe, the orientation is always 1, 2. We number the bottom of the column as 1 and the top of the column as 2. So all the faces at the bottom are having subscripts 1. So L1, V1. And in the case of the streams or the faces on top of the column, then they are both labeled with subscript 2. That's in the case of McCabe. Okay, so it's very important that when you use a particular formula taken from a particular reference, you know the difference of the representation of the variables and the parameters. That way you won't, shall I say, confuse the streams. Now for stripping, so since our solvent here is the gas phase, it's not anymore the feed because our feed here is the liquid phase. So this is where your stage 1 is. So wherever is your solvent being introduced or fed in the part of your column, that would be plate or stage 1. So this is why you have stage 1 here. So the same principle applies. You label the streams or the phases based on the plate where they came from. So for stripping, we have 1 at the bottom and we have N on top of the column. But for McCabe, it's still 1 at the bottom and 2 on top. Okay, we don't change that in McCabe. So the same numbering of the phases. Okay, so these are our types of columns. So we have the tray columns here, or the trade columns. We have the pack column. I've mentioned them. This is the spray column. This is the bubble column. And the modified centrifugal contactor. In all of these particular columns or equipments where gas absorption or stripping is facilitated, vapor is always introduced at the bottom and liquid is introduced on top. That's very important, okay, for you to know. So that's fundamental. So my main goal here is that you are refreshed again of the fundamentals, because I'm sure you will have a lot of problems later on that you will just be simply solving. So it's important that the principles are reviewed and clear to you. When you do a material balance, in the case of gas absorption or stripping, if it's just single stage, this is how we label it. Of course, we have LO and V1 here, and we have V2 and L1 here. The phases that are in the phases rather that are leaving a particular stage are the phases that are equilibrated. Take note of that. So it's B1 and L1 that are equilibrated when they leave stage 1 or this particular single stage system. Your V2 and your LO are the feed phases. So actually your feed is really V2 when you speak of gas absorption, and LO is your solvent. Vice versa if we talk about stripping. Your feed in stripping is this one, the L, and your solvent is the V. Now we do material balance, very simple. You add, you take the sum of the phases that enters your equipment, and you take the sum of the phases that leave your equipment. And as well, we label the resulting phases when these two are mixed as the bulk phase M, where your interface is developed, where real mass transfer occur. Now, if you're now going to make component balance, you can only make component balance once. So if it's based on component C, then let it be a C. You cannot make another component balance based on A because you won't be able to solve whatever is required by using more than one component balance. The component balance equation in terms of pattern takes it from the total mass balance. Sorry, this is not mass balance, but rather mole balance because we're using moles here. So your L and V here will be multiplied to the mole fractions in the liquid and in the vapor phases represented by X and Y. So if you have your component balance based on C, if it's based on C, then your subscript will have the C. If it's based on A, your subscript will have the A followed by the number of the plate or stage where this particular phase here, where our X and Y is multiplied to, is coming from. Okay, so we need to specify the component in which a particular mole fraction is based on, and also at the same time identify where it come from. Okay, so if it's coming from from stage 1 or plate 1, so that is why you have two subscripts for X and Y, one for the component that was used as a basis and one for the plate or stage where it came from. Okay, so if we have for a problem determining the unknown using only material balance and component balance, you have an alternative equation. Both McCabe and John Kuplis uses this, that uses the inert amount of the phases. So in the case of the liquid phase, the inert liquid is water. So let's say if your solvent is pure water most of the time, and it doesn't contain the A, then whatever is the entire amount supplied, that is also equal to L prime. For V prime, that's the amount of moles of air present in your gas mixture. Oftentimes, class is just air with another gas. So we take out the other gas from the air, of course, to purify it. And the liquid that we use for that is water. Okay, V prime then would be the total amount of the gas mixture that is fed into your tower, gas absorption tower, multiplied to 1 minus the mole fraction of A in the feed gas. Then that would be your V prime. Okay? So in here, if you notice, you only have to take note of two amounts, the L prime and the V prime. You need not know the LO, the L1, the V1, and the V sub n plus 1. So you only need to take note of two, L prime and V prime. Another thing is you're not using here, you're not multiplying the inert streams by mole fractions, but rather you're multiplying it with mole ratios. Anyway, it's written here. So this is already a mole ratio because automatically if we have a two-component system, if we have XAO in the numerator in the case of LO stream here, which is just L prime because we're interested in its inert part, then your denominator is 1 minus XAO, meaning this refers to XB sub O. XAO over 1 minus XAO is XB sub O. The same thing in here. So we're using mole ratios, not mole fractions, and they are multiplied to the inert amounts of the streams. This most of the time very beneficial to use in terms of problems wherein the original component balance equation will not help us determine all unknowns. Okay, so sometimes we use the total mass, mole balance or material balance equation, and this one. Okay, mole balance. It's not mass balance class because we are using moles here in gas absorption. Now, this is a sample problem and that's the solution to the problem. So we'll skip that. We'll go to multi-stage processes. So the material balance that was shown to you is for a single stage process. The same actually principle applies for a multi-stage process. So you have your stage 1 to stage capital N, and the small letter n refers to a particular stage in our multi-stage process. So the labeling, notice that's the same as single stage processes. The streams that lives a particular stage are having the subscripts equal to that stage number. Okay? And these particular streams are the ones that are said to be equilibrated. So looking at it, if you do material balance, you will have L sub O, V sub N plus 1, and V sub 1 and L sub N. Okay? And your component balance would still be patterned after your total mole balance. Now for a tray tower, this is I think taken from, if I'm not mistaken, this is taken from John Cook's in the manner the figure is represented. So look at in even the manner in which the streams are labeled. So this is your material balance in an absorption tray tower. So look at the way the faces are labeled and the corresponding mole fractions. So this is our tray tower. Now, if it's a pack tower, it's the same actually as the tray. Same labeling. You can see the labeling here. But, by the way, sorry, I took this from John Cook's also, but this time he used the representation of McCabe. So John Cook's also uses the equation of McCabe, especially if he intends to use the component material balance utilizing the L primes and the V primes, so that he will only have to take note of two subscripts in the X and Y. That is only 1 and 2. So notice at the bottom of the column you have 1, and at the top of the column you have 2. This is how McCabe represents it. Okay, this equation is found in your handbook. I have indicated it in here. Now for the rest of the equations, which I haven't indicated the equivalent in your handbook, please take note of those equations. Or I hope by now you have already marked your handbook as to the equivalent of those equations that you can find in your books, John Cook's and McCabe, because we're using the two. Now, for pack column design, we have the graphical approach wherein you need to write down the operating line for your column. So the operating line uses the mole fractions at the bottom and at the top of the column. And if you notice, class, the labeling here is again based on McCabe, because you only have X1, Y1, X2, Y2. This is how McCabe labels. So this Y1 and X1 is for the bottom of the tower, so tower bottom, and your Y2, X2 is for the top of the tower. Whenever you have plotted your operating line, side by side the equilibrium curve, if it's a gas absorption process, it should be located below the equilibrium line of curve. So this is for gas absorption, and This is for stripping, and the one on top is for gas absorption. Okay, on top is gas absorption and below is stripping. In terms of the location of the operating lines, how are they plotted? You use the x1, y1, x2, y2 as the coordinates. Now, how do we determine the number of stages? We will not, of course, discuss the graphical approach. This is just pinpointing to you the location. So we'll be using the Crimser equation, and look at the manner in which John Kuplis writes the formula. So again, he went back for gas absorption. He went back to the original representation of the streams, which has n plus 1, 1, and 0. Okay, so you have here the mole fraction of the gas phase that enters the column. This is the mole fraction of the gas phase that leaves the column. And you have here the slope of the equilibrium curve or line. So again, this is the slope of the equilibrium curve or the line. If you have a problem concerning the slope of a curve, because if it's a curve, the slope of course will not be a constant, you have to get the slope at the dilute end of the column. The dilute end of the column, where is the dilute end of the column? So I'd like to use this illustration so you will know the dilute end of the column. So the dilute end of the column for gas absorption is the tower top, and the dilute end for stripping is the tower bottom. Okay, the concentrations which are less is the dilute end. So if you're given a curve, just like in this two, you're given a curve, what particular slope will you substitute? Will you substitute for the M? You will substitute the slope of the dilute end. So in that case, you will just have to approximate class. What you do if this is given is actually project this part in here on the curve and determine the slope in this part of the curve. If you're given a table of values for x and y, then you just determine the corresponding slope at this particular point for your x and y in here. Now, if it's for the stripping, you project this one and you have this one here, and then draw a tangential line and get the slope of that tangential line. That would then be the slope of the equilibrium curve at the dilute end of the column. Okay, let me clear my marking. So that's the M that you're going to place in here. XO, of course, is the liquid phase mole fraction of the solvent. Okay, XO is for the solvent. What is this A? That is the absorption factor, the gas absorption factor with the value equal to L over V divided by M. Now, if you have a curve, automatically class, even if sometimes, if you could remember, I suggested that even if you have drawn your operating lines, you could see that it's straight. But you don't know that in between in here, you're not certain that your operating line would be straight through and through. And since there is a possibility that your operating line will not be a line, but could also be a curve, just like your equilibrium line, because these two are different. These are operating lines, and these are your equilibrium curves. It is suggested that you get if you can recall, you get the A1 and the A2. This is the gas absorption factor at the tower bottom. So this is equivalent to L1 over M V1 if you're using the subscript L1 for the bottom of the column. And then A2 is equal to L2 over M V2. What would you do with this? You'd solve separately and get its geometric mean. So you have A1, A2, take the product of that. That should be the A that should be substituted in here. it is always suggested. So if you found out that your A1 and your A2 are just the same, so good, then your assumption that you are really that you have an operating line, not an operating curve, is correct. If not, then use whatever is the corresponding answer when you get the mean of the absorption factor at the tower bottom and top. Okay, so that's it in the case of finding the A. So this one is the slope of the dilute end. This one is the mean absorption factor. If our A is equal to 1, then we have a simplified manner of determining the number of stages or plates. So it would just be dependent on the mole fraction of the feed gas and that of the gas that leaves the tower, and then the mole fraction of the liquid solvent that is used, because this is XO. Now, when A is 1, when your gas absorption factor is 1 or your absorption factor is 1, that tells you that your equilibrium curve and your equilibrium line are parallel. So this one, by the way, is the slope of the operating line. The M is the slope of the equilibrium curve. If it's 1, if A is 1, that tells you that their slopes are equal. If their slopes are equal, then the two is said to be parallel. Okay, so that's fundamental. So that should not be forgotten. So this is the Krimser equation that determines the number of stages analytically, both for gas absorption and stripping. There's a corresponding equivalent for stripping that I will show to you. But in terms of form only, they're similar. Okay, so here, if the equilibrium line is curved, M and A will vary. So M will be the slope of the equilibrium line on the dilute end, so stated already, and A will be the geometric average. Okay, so the labeling here is based on the original labeling, which is that of John Couples L1, V1, L and V sub n plus 1. In here, at the top of the column, it's LO that is being used. B1 is the gas phase that leaves the top of the column. Okay, so that's it for gas absorption. For stripping, it's comparable in terms of form to the gas absorption formula. We just change the y's here to x, and we have here the x changed to y. So this is now your mole fraction of the solvent. We know in stripping that the gas this time is the solvent. So that is why you have your y sub n plus 1. And your liquid is, of course, the feed. So these are the corresponding mole fractions that you need to substitute here. Now, the stripping factor is equivalent to 1 over A. So meaning, the formula that is given to you here for A, for stripping factor, that would be MP over L. Because your stripping factor S is just 1 over A. So you just take the reciprocal of this. In the same manner that you have taken the geometric mean of the A to be sure whether your operating line would be straight or curved, you do the same for stripping. So you don't assume that your S at the bottom and at the top of your column will be equal at all times. So just solve for it anyhow when they are just the same, so good. You have a straight operating line. If they're not, then you need all the more to consider the variation in the slope. So you need to get the geometric mean. The equivalent of the Krimser equation in your handbook is this, equation 14-14, and for gas absorption, it's 14-33. And we have this sample problem here, which I will discuss also later if I'm done with this set of slides. Now, for the design of the tower, so it really depends whether you have a packed tower or you have a tray tower. So for a packed tower design, requiring you to determine the minimum solvent requirement, what is done actually is this. So in the case of gas absorption, if this is your original operating line, you move your top portion of the operating line tangential to, or you just transfer this point here to horizontally to this part here in your equilibrium curve. At this condition, or at this particular operating line, you are at a condition wherein your column is using the minimum solvent, the minimum amount of solvent to achieve the desired separation. So you see here that this is your corresponding, I'd like to project it so you would see. This is the corresponding maximum mole fraction in the liquid phase, where at the bottom of your column, the maximum mole fraction that your minimum solvent amount can take, or can achieve rather, from your feed gas or from the given design of operation. So this Y1, remember the Y1 is the mole fraction of the feed gas. So you move it horizontally here on the equilibrium curve. That will help you determine the X1 maximum, the maximum amount of solute that your liquid solvent was able to carry at the minimum solvent requirement. We do the same when we have, we're talking about stripping here. Your your original operating line has this orientation. So instead of moving horizontally, here you move horizontally. In this case, you move it vertically. Okay, to determine the maximum amount of solute that your this time that your gas can get from your the maximum amount of solute that your gas can take away from the liquid phase. As such, it's now the mole fraction of that particular component that you are determining in your gas phase. Okay, now in this scenario, what we do usually, class, is this. I hope you can still remember. The problem oftentimes will give you the equilibrium equation, like y is equal to mx. Okay, there's a corresponding number here. For example, y is equal to 1.2x. This is the governing equilibrium relationship between xa and ya at any particular time. So what we do to determine the x1 maximum or the y2 maximum, we use this equation and determine the unknown. In the case of gas absorption, if it's gas absorption, you use Y1. So for example, in this case, I'll use Y1 divided by 1.2, and that would be my X1 maximum. And this is the value of the X1 that I will place in my either component balance equation, the original, or the component balance equation that uses the inert amounts of the phases. So depending on what particular component balance I am using. So I hope you have recalled this procedure. So you use the Y1 that you have divided by the slope of the given equilibrium equation, and you'll be able to get X1 maximum without really using this particular equilibrium diagram, or without having to look for this equilibrium diagram and do the graphical thing. If you are given this, you can determine it right away. The same thing is true when you have stripping. So in the case of stripping, same thing. Let's say Y2 maximum, that's the unknown. And let's say with my example 1.2, you use the X2, whatever is the value of the X2. So you'll be able to get the Y2 maximum without doing it graphically. So substitute it in the component balance equation, whichever of the two forms you are using. That way, you can determine the minimum solvent requirement. I hope you have recalled that particular process then when you determine the minimum solvent requirement. If you already have the minimum solvent requirement, I'm not sure if I have placed it in here. If you are required for the optimum solvent requirement from the minimum, you simply multiply it by 1.5. Okay? I think we've discussed it also last year. So kung may minimum solvent requirement ka na, then you can determine the optimum, if it's the optimum that is required. How do you determine the minimum solvent requirement? If you go back here, I'll just go back to that equation for easy recall. This one. So if it's the gas absorption, you are actually determining the L prime minimum. This one, the L prime minimum. This you need to substitute properly, and the X1 that you solve, you place it here. The rest also you place the values. You'll be able to get the L prime minimum. It's different when it's stripping, because if it's stripping, then it's your V prime minimum that you're going to determine. Okay, so just place it in here. Oftentimes, class, this is the equation that is being used because it does not require all four phases to be known. Now, if your liquid phase is not pure water, the L prime minimum that you have here, for example, you already determined the L prime minimum to be, example, 100. If it's already 100, it's not yet the answer. Because if it will require the minimum solvent requirement, and if your solvent has certain amount of A, for example, it's really requiring you to give the L minimum. So L minimum times 1 minus XAO is equal to L prime minimum. The amount that does not contain the A is this, right? That's your L prime minimum. So if you got 100 already, so 100 divided by 1 minus XAO will give you the true minimum amount of the solvent, which has the presence of the A. Your answer here will be good only if you're given pure water as the solvent. But if your solvent is not pure water, you really have to determine the actual L minimum. Because the problem will not ask you for the minimum amount of the inert solvent. It will just be asking you what's the minimum amount of the solvent. So this is not yet your answer. You have to use this equation to get to the L minimum. The same true with the V prime minimum. If it has the presence of A already that needs to be taken from the liquid phase, do that. You use this equation. This time you use here Y. Y, A, N plus 1. Because that's where you are, for your feed, solvent, it's in on top, it's in the bottom, so that would be yes. 1 minus Y A, Y sub A, N plus 1. If it's stripping, by the way, we don't label it N plus 1 because we start with 1 at the bottom. So this should be class YAO in terms of representing it as that of John Cook list. But if it's just simply 1 and 2 at the bottom of the tower, so if it's V minimum, that would be, or V prime minimum, that would be V minimum times 1 minus a YA1. That is if your column is labeled 1 at the bottom and 2 on top. What I like about the labeling of 1 and 2 is you don't have to think of 1 and n plus 1, 0, that is. You simply have to think that the bottom has 1 and the top has 2. So this would be your formula for determining the V minimum, the actual V minimum, if your solvent in stripping has already the presence of A, meaning it's not pure solvent. Okay? In some cases, the representation of McCabe really proves to be more, shall I say, to be not prone to confusion in terms of representation. Why am I saying this? Because if you go back to the representation of John Couples, I'm just suggesting that you use okay. The representation here is this one. So then I will project this. The corresponding mole fraction here, which will confuse some, will be YAO. This would be XA1. This would be YAN. And this would be XAN plus 1. So some will find it confusing, whereas if you simply have 1 here and 2, you need not confuse anything. This will have YA1, this will have XA1, this will have YA2, and this will have XA2. But again, just a suggestion. That is why even John Couples, when he presented the component balance using the inlet streams, he's not using this representation. He's not using this. He's using simply the 1 and the 2 subscripts. Not using the n plus 1, and the 0 subscripts. Okay? So that's it. I will clear my markings here. And then we proceed to the next part. Excuse me, class. Okay, I'll go back to where we paused. Okay, we can have a 5-minute break, class, and then go back here. Okay, 5 minutes. It's 10:35 here. We'll come back at 10:40. So to continue on minimum solvent requirements, so here are the generalizations. Recovery X1 in the case of gas absorption is at the maximum when the inert solvent flow rate is minimum. So you are determining based on the component balance equation using the inert streams the L prime minimum only. So if again, to emphasize, if you determine the minimum solvent requirement and your solvent already has the A on it, or the component that is to be taken from the gas phase, then you need to really solve for the L minimum after you have done solving the L prime minimum. The same is true for stripping. So your recovery Y2 is a maximum when inert solvent flow rate is minimum, represented by B prime minimum. The actual liquid to gas ratio, the liquid to gas ratio, we call this the solvent circulation rate, normally will be greater than the minimum by as much as 20 to 100%. So optimization of the liquid to gas ratio in terms of total annual cost often suggests that the molar liquid to gas ratio, the LM, over G sub M should be about 1.2 to 1.5 times the theoretical minimum. So this is what I'm saying. So if you have determined already the minimum solvent requirement and you are asked for the optimum solvent requirement, we are using class the maximum in the range here. So we multiply it by 1.5 because 20% more than the minimum is the lowest value in the range. But when we do solving, we actually multiply it by 1.5. For stripping, the actual value of the G sub M to L sub M is 20 to 50% higher than the minimum, which is the same as that in gas absorption. Again, using 50% more than the computed minimum based on the inert component balance equation. To illustrate the use of the concept on determining the minimum solvent requirement, so you have this sample problem, and I have already placed in here the, shall I say, the solution. Now we go to the pack tower. As to the design of the pack tower, the liquid is introduced here, gas is introduced in here. And these are the different random packing materials. If you have time, you can view in YouTube the chemical engineering encyclopedia, chemical engineering equipment encyclopedia. You can search it there, and you'll be able to see in a video the actual packing materials, the random and the structured packing materials, and how they ensure that your faces are contacted. So these are your random packing material, and these are your structured packing material. As for the tray tower, so you have the trays, there's no need for the packing materials. I mentioned already that this is the downcomer. The liquid flows in this manner, going down here, horizontally in here, and in here. So the gas flows upward. As for the tray tower, the openings can either be in the form of perforations. In the case of the simple sieve tray tower, it can have also the valve caps. It can have the bubble caps. And this is an example of a tray with valve caps. You'll be able to see as well videos on this in YouTube on how these different types of opening in your tray tower operates. Now let's go to the design of the column. So in designing our column, whether it's the absorption column or the stripping column, we are interested with determining the diameter and the height of the column. So let's first know the procedure in determining the diameter. So for the diameter, we need to determine the pressure drop. So in Jean Couplis, there's a need for us to determine the pressure drop, the flooding velocity, and ultimately determine the tower diameter. This is for a pack tower. So the usual design is 60 to 80% of the flooding velocity being used. In this time class, in the range of 60 to 80%, we're using the least in the range, the least value in the range, which is 60%. If you can recall, we determine the flooding velocity and we multiply it by 60%. And that's our basis for our tower diameter. Okay, there is a sample problem as well in Jean Couplis on how we determine the tower diameter using 60% of the flooding velocity. Associated with the flooding velocity and the tower diameter is the determination of the pressure drop. Okay, for packed and structure for random and structured packing materials, this should be random class. This is your packing factor, the F sub P, and they are taken from a table. Your handbook has a very comprehensive table in terms of this packing factor for different types of packing material. So what we have in our book in Jean Couplis is only around 10 for each of the types of packing material. I'm referring to random and structured packing, but your handbook have several pages on this regarding the different packing materials for the different types of regarding this packing factor for the different types of the packing material. Please check on it on the topic on gas absorption. Now you need the packing factor, that way you will determine the pressure drop at flooding. So when your column is flooded already, this is the corresponding pressure drop, the delta P. Now, the procedure in determining the column diameter and pressure drop is you first obtain the packing factor, which is taken from the table, then find the flooding pressure drop. So the pressure drop delta P is given by 0.115 times the packing factor raised to 0.7. So find the corresponding flooding gas velocity using the pressure drop correlation. So I'll be showing to you the diagram later. So because we have a different diagram for random packing and different for structured packing, we have the same diagram in your handbook also. You are to get from this table the corresponding flooding velocity. And once you have already the flooding velocity, multiply it by 0.6 so that you can determine your tower diameter. Choose diameter such that the gas velocity is about half of this. Now, this is just but a suggestion, but in the sample problems in John Couples, it's more than half. It's 60% actually. Then you find the pressure drop in the column from the pressure drop correlation figure. The table that I was mentioning, which is more detailed, is this one. If I can project this in your handbook. So you have here on the upper portion the random packing, and you have here the structured packing, and you have one of the columns here, the packing factor, this one. So one unit is in per foot, the other one is per meter. So depending on the set units that your problem is working on. Okay. In your handbook, you have this also. And for the pressure drop correlation, I'd like to project this. So for random packing, this is, we determine the flow parameter. I hope you can still remember. And from the pressure drop correlation, we have this one, the values here. If the value that you got is not amongst the curve here, what you do is just approximate the curve. Then you'll be able to determine the capacity parameter. In your capacity parameter, in here, you'll be able to get the B sub G, which is the linear velocity at flooding. You multiply it by 0.60, that way that's the one that you're going to use in determining the diameter of the column. So this one is for a random packing material. You have also one for structured packing material, but same thing, same procedure. Okay, you determine the flow parameter to get the capacity parameter. So this is the one I'm referring to. So this one is for structured packing. And just like what I've mentioned a while ago, these are your delta P curves. So first determine the delta P as suggested in the steps in determining the diameter of your column. Okay? So determine the flow parameter to get the capacity parameter to get the linear velocity at flooding. What about for tray tower? Because this one, this procedure that is given you here, which needs the delta P to be able to use this flooding correlation diagrams, is only for pack towers. So if it's a tray tower, this would be the procedure in determining the diameter. So obtain the tray factor, the K sub P from the figure. This is the figure given in John Couples. Find this table equivalent in your handbook. Okay? Instead of the delta P in the curves, you have the tray spacing here. Okay? With the tray spacing and with this value prior solved beforehand, you can get here the K sub V in step 1 that is stated in here, the tray factor. Then, wait, my internet is unstable. Then find the entrainment gas velocity from equation 11.5-14. Occurs just before flooding. So this uses the fair color correlation, and this is the formula. If you have saved the set of slides that were given to you last year in the topic of gas absorption and stripping, you will also see the same formula shared to you. So the typical value for the maximum linear velocity for tray towers is 3 meters per second. So meaning more or less the value that you should be able to solve will be within this value range. Okay. Now for the value of the sigma in here, you have 20 dyne per centimeter. This is the interfacial tension rather. So for organic liquids, including water, so it's 20 dyne per centimeter and 72 for water. Now you choose diameter so that gas velocity is about 0.70 of the V maximum. If you're using for packed column 60% of the V for flooding, in here based on the formula of FAIR, you use 70% of the V maximum that you have computed. That way, you have a basis in determining your tray tower diameter. Now, pressure drop usually is much larger than in packed columns. That is why when we were discussing the topic, your packed column is preferred for delta P's, which are small. And we have delta P here equal to delta P dry plus raw LGH or raw sub LGH. This is still pressure. So delta P dry is the pressure drop through the holes of the tray, and H the sum of liquid levels on all trays, which is about 10% of the column height. Now, you'll be able to see a sample problem on this in Jan Kuplis, just one, on the use of the flooding velocity to determine the diameter of a tray tower. Okay, so please check on that. And this is that particular diagram where you can get the tray factor. Now that's for the diameter. As for the height of the column, we have a lot of formulas for the height of the column depending on the service. What is the particular service of your column where it is used. Okay, so but nonetheless, in terms of the height, if you use the Z as a representation for the height, whether of your absorption tower or your stripping tower, you have these choices. You have HG, or H sub G, N sub G, H sub L, N sub L, or if it's based on the number of overall liquid phase transfer units or overall gas phase transfer units, you will use the Hall knot. Now, this has, you can find this in equation 14-15 in your hand. The nog and the null, the number of transfer units, the overall number of transfer units in the gas phase for the nog, the null for the liquid phase is comparable to the equation we have discussed a while ago, the Crimser equation. So if you have this two, you just multiply it with the hog and the nog. Now the hog and the null rather, you have it in here. In your handbook, the nog and the null are these equations, and the hog and the hull is these equations, because they are paired together to determine the Z. Okay, so please check on your handbook these equations. Now from John Kuplis, the Philippine edition, that is, computing for the tower height Z using the film of overall mass transfer coefficient depends on whether you are given a dilute solution or the concentrated solution. So please check on this if you have an available time in John Kuplis as to this equation and its equivalent, if there's any, in your handbook. Okay, determining the Z based on whether your feed solution is dilute or concentration. Now, concentrated rather. How do we know that our solution is dilute if the concentration is less than or equal to 10%? Beyond that, your solution is said to be concentrated already. Okay? Now, the HETP is used for packed towers. Okay? HETP is defined as the height of packing equivalent to one theoretical stage. It's the height of the packing material that was used, which is equivalent to one theoretical stage. Now for HETP, in terms of the hog, if you have already the hog, then you just need the absorption factor. And you have here the NUG in terms of the absorption factor and the theoretical number of stages. So if you have determined the theoretical number of stages, you can determine the NUG. And if you have the HUG, then you can have the 2 multiplied to get the Z. But if you want to convert from the HUG to HETP, because HETP uses only the theoretical number of stages to get the Z, then you can use the HUG to convert it to HETP. And then determine with the N, you can determine also your tower height or your column height if you have a packed tower. Now this Z, which uses the formula N times HETP, is the same for both packed and tray tower in a condition we say that the operating line and the equilibrium line is said to be parallel. So the Z for the tray and packed tower is the same when the operating line and the equilibrium line are said to be parallel. So other conditions, of course, they're not the same anymore. Okay, you have this sample problem. You have this sample problem on the determination of the tower height. And the detailed solution to this problem is in here. So if I'm going to share it to you, if this is clicked, you have the corresponding PDF file. But I will share as well separately the file to you just in case you won't be able to open it later when it is shared already in Canvas. Okay, that's in terms of sample problem to use in determining the tower height. Since you have already ample examples in John Kupris as to determining the diameter for your pack or tray tower. Okay, now we go to the last topic here in this set of slides, which is, I think this is not yet the last. This is second to the last. We go to adsorption. Adsorption. Adsorbed. So adsorption is not the same as absorption. So that is why I discussed this right after absorption. So this is a process in which a component of a gas or liquid are adsorbed on the surface of the adsorbent. So the adsorbent is usually placed in a fixed bed. Okay, your adsorbent is placed in a fixed bed, and then your component to be adsorbed on it is the one that is fed onto the bed, that so that the components need only to be adsorbed on the surfaces of these adsorbents. The fluid is passed through the bed where solid particles adsorb component from the liquid, stated already, and the saturated adsorbent is regenerated and used again in the operation. So there is the regeneration of the solid adsorbent, that way it can be used again. Now the application of adsorption. So in liquid phase adsorption, we have the separation of paraffins from aromatics, or the separation of fructose from glucose. In the case of gas phase adsorption, so we can have the removal of H2S, CS2 and other odorous compounds from air, and the removal of organic solvents of paints in air. These are just one of the many, of course, application of adsorption. As for the adsorbents, so they are one that accomplishes the process of separating the component from the liquid or the gas phase. So these are artificial and naturally occurring solids, which a highly developed with a highly developed surface, which readily adsorbs matter from solutions surrounding the adsorbent bed. So the adsorpted process of an adsorbent depends on its chemical composition, its physical surface condition, the degree of its porosity, and its specific surface area. So how well is the adsorbent in performing its duty depends on these 4 factors. Adsorbents must have high abrasive resistance, high thermal stability, so even if their corresponding temperature changes, it should remain stable, and small pore diameters. And they should have distinct pore structures. Okay, these are there should be their characteristics. So most industrial adsorbents fall into one of the three classes. So oxygen-containing compounds. So they are typically hydrophilic and polar, including materials such as silica gel and zeolites. So carbon-based compounds, on the other hand, are typically hydrophobic and non-polar, including materials such as activated carbon and graphite. What about polymer-based compounds that are used as adsorbents? They are either polar or non-polar functioning groups with a porous polymer matrix. So these are the three types of adsorbents that are being used. So let's look into them one by one. So the activated carbon, it's not costly, it's common. So a highly adsorbent powdered form of carbon made by thermal decomposition of wood, coconut shells, palm shells, oil husk, and sawdust. So surface area ranges from 300 to 1,200 meters squared per gram with an average pore diameter of 10 to 60 angstrom. Now, application. So, groundwater purification. I'm sure you know this. Dechlorination of processed water. Water purification for the use in swimming, in pools, and the polishing of treated effluents. The second most popular is the silica gel. We have this in packagings actually. So these are granular and porous form of silicon dioxide made by acid treatment of sodium silicate solution to produce gelatinous precipitate that is washed, then dehydrated. Surface area is even higher, 600 to 800 square meter per gram with an average pore diameter of 10 to 50 angstrom. So I forgot to place the unit. So applications used for drying of processed air, adsorption of heavy hydrocarbons from natural gas, and most of the time used as a drying agent. So it's moisture absorber. Now we have activated alumina, highly porous material manufactured by hydrated aluminum oxide by heating to drive off the water. So surface area is 200 to 500 square meter per gram with an average pore diameter of 20 to 140 angstrom. So the activated alumina find its application in catalyst applications and fluoride adsorbent. Then we have the molecular sieve zeolites. So these are microporous aluminosilicate minerals that form an open crystal lattice containing precisely uniform pores. So different zeolites have pore sizes from 3 to 10 angstrom. So again, application is in drying of processed air, CO2 removal from natural gas, CO removal from reforming gas, air separation, catalytic cracking, and catalytic synthesis and reforming. The last here is the synthetic polymers or resins. So synthetic polymers or resins are made by polymerizing two major types of monomers, which are aromatics and acrylic. So they are used to decolorize sugar solution, take note, and the recovery of antibiotics from plant extracts and proteins. Now, the concentration pattern in the fixed bed. So what is the concentration pattern in fixed bed where this liquid or gas feeds are being processed that way? The components need to only to be adsorbed on the fixed beds or solids. So concentration in the fluid phase and in the solid phase changes with time as expected, as well as with position in the bed. So as the fluid flows through the bed, one position concentration is different from another. Let's say point to point concentration is different. The same thing with, of course, the time. Because as time proceeds, the position of the solution or the phase in the bed changes also. So most of the mass transfer here occur near the inlet of the bed where the fluid first contacts the adsorbent. So there is much degree of adsorption at the inlet part of the bed. After some time, most of the mass transfer occur farther from the inlet since the solid near the inlet is already saturated. So in our language na nagamit na ang tanan nga exposed surface sa aton nga adsorbers at the inlet part, so it cannot anymore absorb components from the phase that is being processed. So that is why most of the transfer occur already in the farther part from the inlet because the adsorbers are already at the inlet portion is already saturated. Region where most of the change in the concentration occur is the mass transfer zone. And this is the concentration profile in fixed beds. So you have here the height of adsorption in the bed. So this is height 1, height 2, height 3, and height 4. Height sub T total measured from in here. This is 0 height. And this is the ratio of the concentration at any particular time T over the initial concentration. So the profile goes like this. And you have here, at this particular portion, you have the ratio of the equilibrium concentration to the initial concentration of the phase that is to be processed in the bed. And you have here the corresponding time for this particular height to be saturated. So this is T sub 1 for this height. This is T sub 2, T sub 3 here, and you have T sub 4. For the breakthrough point, this is being mentioned in the process of adsorption. That is the point wherein the maximum concentration can be discarded. So in here, you have 0.01 to 0.05 of the feed concentration that is discarded already. So that's the breakthrough point. As the breakthrough continues, this is the breakthrough point. As the breakthrough continues, the concentration of the adsorbate in the effluent increases gradually up to the point C sub D. Okay, the adsorbate is already the liquid that is freed of the, shall I say, of the components because you have the components already adhering on the adsorbents. So shall we say the adsorbate is already the process phase that has passed through your adsorbents. Okay. Now, what are the very important adsorption principles that you are to take note of? So since the width of the mass transfer zone does not change, effect of the moderate changes in the feed concentration to breakthrough point can be determined. Now, adsorbents are scaled up from laboratory tests in a small diameter bed, and the large unit is designed for the same particle size and superficial velocity. So what is done initially, class, is the process of adsorption is then first done in the lab. Then it's just being scaled up using the same particle size and superficial velocity. Now, the scale-up principle is that the amount of the unused solid or the length of the unused bed does not change with total bed length. So in terms of ratio and proportion, the unused solid or the length of the unused bed, whether we have a small length of absorber or we have one already designed for industrial application, should not change. That is ratio of the unused solid or length of the unused bed to the total bed length. Okay, so it's still done, let's say, trial in the lab, and then it's just being scaled up in the industry. The formula that you can use here is this one, determining the breakpoint time. So this is the time wherein you have already 1 to 5% of solids present in your adsorbate. So meaning gamay-gamay na lang gid ang nabilin mo nga component nga nabilin sa imo adsorbent kana adsorbate because na-adsorb na siya sa adsorbent. So 0.01 to 0.05 or 1 to 5% only, and it's ready to be discarded already. When is that time when you are ready to discard it? Because you're, in terms of concentration, it already reached 1 to 5%. That's the breakpoint time. Determining it needs the time when C over CO equal to 0.5. So the highest value in the range of concentration, point, this is 0.05 class. Maybe I've got mistaken here. It should be 1% to 5%. It's here, 0.01 to 0.05 of feed concentration. So there's a typo here. This should be 0.05. Now, LUB is the length of the unused bed and L is the total bed length. So if this is done in the lab, this ratio of the unused bed length to total bed length should be the same with that in the industry to determine the breakpoint time based on this ratio of the final concentration to initial, which is 0.05, not 0.5. Now, so in terms of the ratio of H sub B to H sub T, where H sub B is the length of the bed used to break point, and H sub T is the total bed length, that would be the same as to the time ratio. So fraction of the total bed capacity utilized to break point. So H sub B over H sub T is equal to this fraction of the total bed capacity utilized up to break point. That's in the case of adsorption. Now, in terms of adsorption, we have batch adsorption. So this is often used to adsorb solutes from liquid solutions when the quantities treated are just but small. So consists of contacting an adsorbent with another material for a given period of time. And at equilibrium, this is the amount of the solute adsorbed per amount of adsorbent, which is the Q. How much of the solute gets adsorbed per unit amount of adsorbent used. So you have the K as a constant, and this is determined experimentally. So this has to be provided in the problem if there is no experimental data given to you to interpret. N is a constant as well, so this is determined experimentally, just like the K, and C is the solute concentration in solution. This is actually very comparable to the rate law in kinetics. This is your rate, and this is your concentration, right? This is your rate constant, and this is the order of the reaction. Both the rate constant and the order of the reaction are determined experimentally. If you recall our discussion then last year, in determining this K and N, we are provided with a pair of data, the Q and the C, and the treatment is very much similar to that, with being given the rate and the concentration in kinetics. That way we can find the N and the K. So this is at equilibrium. So this equation will work in terms of the relationship between solute concentration that remains in the solution, ang wala ma-adsorb, and the amount of solute adsorbed per unit amount of adsorbent used. Okay? Now, there are other formulas actually that will be shown to you in a little while. Now, this material balance equation that I'm sharing to you is a material balance equation taken from Colson. Jan Kuplis has also its own material balance equation. So if you're comfortable with using that of Jan Kuplis or McCabe, then do so. Or more so, better if you have one in the handbook, which you have already looked for, comparable to this. So in here, I have defined everything in here as defined by Colson as well. Your Q sub F is the initial concentration of the solute, and it is to be multiplied to the amount of the adsorbent, M. And C sub F is the initial feed concentration, and S is the volume of the feed solution. So this is for the feed, and this is for the adsorbent. Okay, and then you have here on the other side, still M, amount of adsorbent, but this time it's multiplied to the initial equilibrium, rather, final equilibrium value, because the Q sub F is the initial. Okay, the final equilibrium value times the amount of adsorbent plus the final concentration times the volume of the feed solution. Okay, it's just like input to output. So this side is for the input and this side is for the output. Again, this is taken from Paulson. So if you're not comfortable with this formula shared to you, McCabe has one. I think it's the same as this one if I'm not mistaken. Okay, Mike, John please has one also. Now, we go to fixed bed adsorption. This is widely used method for adsorption of solids from liquids or gases employing a fixed bed of granular particles. Now in here, fluid to be treated usually passes down through the packed bed at a constant flow rate. So the previous equation is for batch adsorption, one passing through, or your phase to be treated with the adsorbent is placed into your adsorber. This one is continuous because your fluid to be treated usually passes down through the packed bed at a constant flow rate. So mass transfer resistances in here are important in the fixed bed process, and process is unsteady state. Now, associated with this adsorption class are the adsorption cycles, and you need to be acquainted with these absorption cycles. So it's with the processing variables. For large-scale adsorption processes, and if we have the cyclic batch system, the adsorption fixed bed is alternately saturated and then regenerated in a cyclic manner. So meaning we pass through the, the feed to be treated on it. Then once the adsorbers are already, shall I say, saturated, it's being regenerated. Then once it's regenerated, it's being used again. So that is why it's a cyclic process. It's saturated, then it's regenerated, then saturated again, then regenerated. For continuous flow systems, this involves a continuous flow of adsorbent countercurrent to the flow of the feed. So this, in this case, in the continuous flow system, so flow, your term here is flow, both this time your adsorbent bed and your fluid to be processed flows countercurrent to each other continuously. Okay? Continuous flow of adsorbent which flows countercurrent to your feed. So this is in the case of large-scale adsorption processes. So the batch system uses the saturation regeneration cycle. Now we go to the cyclic batch system, the one that is mentioned here. So there are 4 basic methods commonly used in fixed beds. So generally, the 4 methods operate with 2 or 3 fixed beds in parallel. So 2 or 3 fixed beds in parallel. Regeneration in the first bed is done using any of the following method. Since the cyclic batch system uses the saturation, regeneration, saturation cycle, then what are the procedures of regenerating the adsorbents in the bed? So these are the following. So these are actually referred to as the adsorption cycle. The temperature swing cycle, we have the pressure swing cycle, we have the inert purge gas stripping cycle, and the displacement purge cycle. So this is how our beds in the cyclic batch system are being regenerated para magamit pa sila ulit. Okay, so let's go to the temperature swing cycle. This is also called the thermal swing cycle. The spent adsorption bed is regenerated by heating it with embedded stream coils or with a hot purge gas to remove the adsorbate. Okay, so since it's already saturated, meaning all exposed surfaces already have adhering solute particles, these adhering solute particles need to be removed. That way, your adsorbent can be used again. So the process of removing is through the use of embedded stream coils or with a hot purge gas stream. Now, the time for regeneration here is a few hours or more, generally, for the temperature swing cycle. So, increases the temperature because you're using the hot purge gas stream or the embedded stream coils to remove the adsorbed solute in the surface of your adsorbents. What about the pressure swing cycle? So, take note the differences of these different regeneration processes for your cyclic batch system. The bed is deserved by reducing the pressure at essentially constant temperature and then purging the bed at this low pressure with a small fraction of the product stream. This process for gases uses a very short cycle time. So the pressure swing cycle is used for gases, adsorbed gases on adsorbents, and it reduces the pressure at constant temperature, after which the bed is purged with the product stream. That is the adsorbate that was discarded already. Now, the time here is also short, just like the temperature cycle. What about the inert purge gas stripping cycle? So the adsorbate is removed by passing a non-absorbing or inert gas through the bed. So you were using here not a heated stream, but rather an inert gas that will remove the adsorbate in your adsorbents. The regeneration cycle times here are usually only a few minutes. So it's a few minutes, but of course this inert gas, the amount of an inert gas, a non-absorbing inert gas, is to be considered, because this is of course another cost, because you're going to look for an inert non-absorbing gas to remove your adsorbate. In the 3 cycles discussed so far, this one is the only one that specified that your cycle time is just a few minutes. Now we go to the last, the displacement purge cycle. The pressure and temperature are essentially constant, so a modification of both the temperature and pressure swing cycle, because this time both temperature and pressure is kept constant. But, so this is similar to in the purge gas stripping. But a gas or liquid is used that is absorbed more strongly than the adsorbate and displaces the adsorbate. So in terms of defining this particular cycle, that term displacement is really appropriate, because an absorbing gas or liquid is being used that will displace the adsorbed solute in your adsorbent. So it will displace the adsorbed solute. So cycle times are usually only a few minutes. So stream stripping is often used in regenerating of solvent recovery systems using activated carbon. So the other term for this is stream stripping. Now it's used in the recovery of activated carbon as adsorbent. Okay? Now we will continue with the rest of this. My time is 11:27. I'll be discussing here the Langmuir isotherm and the Freundlich isotherms in absorption. Then we go to extraction. The next set of slides will be focused on distillation and, if I'm not mistaken, leaching already. Okay? Next week, we'll be using our time schedule. We'll go back to our time schedule, which is Wednesday, 5:30 to 7:30. You have any questions, class?